OS Deadlocks Part 5. In this video, we are going to see deadlock detection and recovery mechanisms. Before moving on to this video, I recommend you to refer back all the 4 parts on deadlocks for better understanding. Let's move in. Here, we are going to detect whether a system is blocked in a deadlock or not. After detecting whether a system is in deadlock state, then we are going to see how to recover from that state. In deadlock detection, there are 2 mechanisms. One is if the resource is a single instance resource, or if the requesting resource is a multiple instance resource. So for these 2 strategies, we will see how to detect a deadlock. When to apply a deadlock detection strategy? When there is a low CPU utilization of the process, then we can move to deadlock detection. The second condition is majority of the process is blocked. In these conditions, we can go for deadlock detections. Instead of doing a deadlock detection for every 10 minutes of time period or every 15 minutes of time period, because if we do that, there will be much CPU overhead, right? So instead of that, if these conditions occur, that is low CPU utilization and majority of the processes are blocked, then we can go for deadlock detection strategies. In this example, we are going to detect whether there is a deadlock using a single instance resource type mechanism. So we have seen this example, right? Already. So this graph is a resource allocation graph. All the resources R1, R2, R3 and R4 and R5, there are 5 resources and all the resources are of single instance resource type, right? So one dot here means it is a single instance resource type. And there are 5 processes requesting all these resources. We will convert the resource allocation graph to wait for graph. So this mechanism we have seen in the previous videos, right? How to convert a resource allocation graph to the wait graph we have seen in part 1 video. So kindly refer to that for better understanding. So here we will see how to convert a resource allocation graph to wait graph. So the resource allocation graph will contain both resources and processes, whereas wait for graph will contain only processes. Let's draw the processes first. Process P1, process P2, process P3, process P4, process P5. So these are all the processes available from the resource allocation graph, right? So I have drawn all the processes. Process 1 is waiting for resource 1, which is held by process 2, right? So process 1 is waiting for process 2. So I'll put an arrow for process 1 and process 2. Similarly, process 2 is waiting for process 5, right, to release the resource of R3. So process 2 is waiting for process 5. Process 2 is waiting for process 3 to release the resource R4. Process 2 is waiting for process 3 to release its resource. Now, process 3 is requesting resource 5, which is held by process 4. So process 3 is waiting for process 4 to release the resource R5. Now, process 4 is waiting for process 1 to release the resource R2, right? So there will be an arrow process 1 from process 4. And then process 2 is also waiting for process 4 to release the resource R5, right? So process 2 is waiting for process 4. This is the wait for graph. Now we have drawn for this resource allocation graph. To detect whether there is a deadlock, we will see whether there is a cycle or not. See here, from P1 to P2, P2 to P3, from P3 to P4, again P4 to P1. There is a cycle, right? So if there is a cycle for a single instance resource type, we have seen this condition, right? It is a deadlock. So this example is a deadlock condition. This is how we detect a deadlock for a single instance resource type. Now let's move on to detect a deadlock with multiple instance resource type. See here, there are multiple instances, right? There are 3 resource types of A, B, C, and the total instance resources for A is 7, B is 2, and C is 6. This one, right? This table, we have already seen that in Banker's algorithm, right? Where only difference is there will be a maximum column. Here, there is no maximum column here. Apart from it, this table looks like a Banker's algorithm. solving problem. To detect a deadlock for a multiple instance resource type, we will run a safety algorithm. So what a safety algorithm is, if there is a safe sequence for all the processes to complete from the available resources, then we can say that there is no deadlock. In the previous video, we have seen, right, deadlock implies unsafe state. If there is a safe state, we can imply there is no deadlock, right? So in this example, we will see whether there is a safe state or not. If there is a safe state, we can say there is no deadlock. If there is no safe state for this example, then there is a deadlock. Yes. So let's see. At time t, there are 5 processes, right? P0, P1, P2, P3, P4. P0 is requesting nothing, right? So it is allocated and it is requesting nothing. So it is not blocked, P0. P1 is allocated 200 and it is requesting 202. But my available resources, current available resources, 000. So P1 gets blocked because request for resource A and resource C will not be satisfied for process P1. So it is blocked. Let's check for process P2. So process P2 request 000, right? So it is not requesting anything. So it is not blocked. It can continue. So process P3 is requesting 100, but my available resource is 000, right? So it will be blocked. Now let's check for process P4. So for process P4, it is requesting 002, but resource C's availability is 0. It is requesting 2 resources of request C. So it is also blocked. We will check for a safe sequence now. So first, either P0 or P2 can finish its task, right? Let's assume the P0 completes its task and release the allocated resources. So my available will become 010 because it is already allocated 010, right? So it will release these resources. So I'll add upon to the availability here. So my current available will become 010. P2 also is not blocked, right? It can complete it and release the allocated resources. It will be added to the availability now. So it becomes 313 because 010 plus 303 will be 313, right? I check whether P1 is blocked currently. Now with this availability, can I satisfy P1's request? Yes, I can satisfy P1's request now. So after P0, I have done P2. Now I can satisfy P1's request. After satisfying P1's request, P1 can complete its job and release its allocated resources. It's 200, right? So I will add 200 with 313. So now my current availability is 513. Can I satisfy P3 now? Yes, we can satisfy it because it's requesting one resource of A only. So I can satisfy P3. So after completing P3, my new available will become 724. Finally, there is one more resource left, right? P4. Can I satisfy the request? 002. Yes, I can satisfy the request, right? After satisfying the request, I will release this allocated resources after completing P4's task. New availability will become 726. See here, after completing all the resources, what I am getting? 726, which was my total resources, right? Initially, that is 726. Fine. So this is one of my safe sequence. So for this example, there is a safe sequence. So there is no deadlock. I can say there is no deadlock with multiple instance resource type. So this is how we detect a deadlock for a single instance resource type and a multiple instance resource type. For single instance resource type, we will draw a wait for graph. So for multiple instance resource type, we will use the safety algorithm to check whether there is a deadlock or not. We will move on to the recovery mechanisms. If we have detected a deadlock, whether in a single instance resource type or in a multiple instance resource type, we will see how to recover from that deadlock situation. So broadly, there are two categories. One is process termination. Other one is resource preemption. We will see what is process termination is. So if there are multiple resources which are waiting for each other to release its resources, and what I do is I kill all the resources and then I restart the system. This is one of the mechanisms. So here, by doing this, my CPU utilization is reduced. So instead of that, I will kill one at a time. Okay, so let's assume there are process P1, P2, some 10 processes are there. Now I will kill, let's say, process Pj. So first I have to decide how to choose a process to kill it, right? There are multiple mechanisms to choose a process to kill it. One is most recently used process can be chosen for killing, or so whichever process has utilized the CPU less, I can choose that process and kill it. So there are many strategies to choose a process and kill that process, right? So after killing it, and then I will restart this process. After killing this process, I will release the resources, right? And then restart this process. So some of the resources will be free so that other process can use that resource and can come out of the deadlock situation. This is how I will recover from a deadlock by process termination. Either I can kill all the process, or I can kill one process at a time and can restart that process. So if I kill all the process, my CPU utilization will be lesser. If I kill one process at a time and restart the system, my CPU utilization will be better when in comparison to killing all the processes. But there is a chance of starvation in both the cases. Why there is a starvation? Actually, I have explained starvation in previous videos. Think of the situation why there can be a starvation and put your thoughts in the comment section. Fine. The second mechanism is resource preemption. What is resource preemption? So if there is a process Pi holding a resource Ri, fine, and process Pj is requesting for resource Ri. Okay. Similarly, process Pj is holding resource Rj and process Pi is requesting for resource Rj. This is the typical deadlock situation, right? We have seen already resource preemption. There are two types. One is forcefully preempt a resource, or it is self-preempting a resource. So there are two strategies which we have seen already. It can take any one of the strategy and can preempt a resource and give that resource to the other process to complete its task. So let's see an example for resource preemption. So here there are three processes, Pi, Pj and Pk, requesting these resources in order. So this is the time axis. Okay. So in this order, it is requesting. Let's say there is a deadlock situation occurring here. There is some code, then it is requesting for resource A, then there is some code requesting for resource B, then there is some code similarly requesting for resource C, then there is some code requesting for resource D, then there is some code, then deadlock happens for PA. Similarly for PJ also, there are some codes in between all the resources. So now deadlock occurs at this situation. What resource preemption do is, it will preempt all the resources Pi, Pj and Pk to the previous request here. So it moves on to this point. Okay. Similarly, it will move on to this point here. So the latest requested resources will be preempted. It will again resume from here. So it will restart from here, right? Again, it moves on here. All the process will move on forward again, requesting all the resources. Right? If there is a deadlock here again, what I'll do is I will preempt here now for all the process Pi, Pj and Pk. Again, I'll resume it. I will restart it from here. Similarly, this continues till the deadlock is recovered. So this is how resource preemption will act upon. So these are all the topics that in deadlock. I hope you understood this video.